So I guess the majority of you has a background in physics. I have a background in math. So I'm happy to be interrupted at any time and have questions so that it's more fun and it's not just me talking for an hour and a half. But please pertain yourself to ask 2 physics questions. So just a step back from what Philip already told us yesterday, small recap. And let's start to think what is a qubit. Everyone has a probably different opinion on that. Let's say that today for me, a qubit is a state that can be described like this as a superposition of 2 basis states, 0 and 1, and the qubit can be in any arbitrary state. And what characterizes a qubit in this picture is that we have some logical operators that are the poly, x, y, and z, and identity. And what is important about these logical operators is that we have relationships among them. So the identity, of course, doesn't do anything to the state of our qubit. So the identity of phi, our qubit state, is phi, as expected. And the crucial other relationship is that x and z anticommute. So what we want to do is to describe a qubit in a way that has the same relationship, the same operators, but is also resilient to error. So in this case, we have no redundancy. And for any error rate, let's suppose that we have a poly operator that is randomly applied with some probability p to our state. If that happens and our qubit is just encoded like this, then there is no way we can detect the presence of an error. We just think that the qubit state to begin with was in another state. So what we do in error correction is we add some redundancy with the goal of reaching an error rate p prime that is less than p that protects our qubit. So we know that we do something, we add redundancy to our state so that we can decrease the probability of error and also add the ability to detect for the presence of that. So to do this, instead of using one qubit to encode one logical bit of information, we're going to use n qubits to encode the same amount. So we're going to have a state that I've called phi bar, but what is important is that we use more than one qubit, like in this case n, this is what the symbol means, to encode one logical bit of information. And what we look for is to find, again, the same relationship that we had before. So we're going to look at operators in Pn, so the poly group on n elements, that is given by the product, tensor product of poly. And we're going to define operators that gives us the same relationship as the identity and the anti-commuting relationship between x and z. So for the identity, we're going to take a commutative group, subgroup of the poly, stabilizer group, here in blue, and we are going to take all the states that are invariant under the action. So we are going to take a set of stabilizers, we call, is a commutative group, and then the states in our code space are going to be all the +1 eigenstate. And what is important is that the stabilizer acts exactly as the identity. And we can do that if the stabilizer group, as Philip told us, is commutative and doesn't contain the identity. Otherwise, everything is empty. And then we're going to look for other poly operator in Pn that respect the same relationship as x and z. So this is the goal. It's the only thing that we care for. Define a set of poly that are the identity on our code state, and then find x and z, other Pauli operator that has the same relationship as poly x and poly z. And we try to do this so that to decrease the error rate, the encoding error rate. And this is the diagram we care about. So we have the poly, we have a stabilizer group that is commutative and that represent identity in our code state, and something a bit thicker that is the set of logical, X and Z logical, that generate the poly, that of course contain the identity, but also acts non-trivially on the code state. And back again, as we have seen yesterday, this is the planar code. So I'm gonna put qubit on each edge of this lattice, and I'm gonna define faces operator and vertex operator in this way. So the faces are Z operator that are supported on a face like this, and the X operator are supported on edges that are incident to a vertex. So I will use orange for Z and blue for X. And when I draw something like this, I mean the operator that has Z support on these 4 qubits and the identity elsewhere. And what is important, just to check, so the identity, we don't know what the state is, but I'm just saying these are the operators that are gonna act as the identity on my code space. And the first thing that I have to check is that they actually commute, right? So identity is the identity, so you should apply the identity left and right, and it should be the same. So, and because X and Z anti-commute, to a poly X and a poly Z operator do commute if and only if they overlap on an even number of positions. And as you can see, on a square lattice, if you take a face and a vertex, you always have even overlap, right? So this is a good definition of identity, and we are happy with that, right? And then we are gonna look for the logical operators. So we are looking for X and Z operator that anti-commute and also commute with identity. That was the rule. So I'm gonna tell you, and we can verify that this is actually a good definition, that an operator like this, supported on these vertical edges of Z, is actually acts as a Z operator together with an X operator that is supported on these edges in a transversal way. And we actually find the relationship that we were looking for, that was X, Z. So we have to check whether these two operators anti-commute or not. And that's easily seen because they only overlap on one qubit. And since X and Z anti-commute, we are good. Not only that, we have to check whether these operators actually commute with the identity. And that it's very easy because if we have orange and orange operators, they are of the same kind. So a bunch of Z always commute with a bunch of Z, similar for the X. And if we check when we have this vertical line here, and we take any vertex operator, this is always gonna overlap on 2 qubits. So we are good. I mean, the logical Z commute with the logical identity on the X part, and similar if we traverse the lattice in this direction, we have the same. So again, this means that we are good. This definition of identity and logical operator is consistent with what we have asked for before. And the other goal that we wanted was to be sure that we added some redundancy, so that the goal is to decrease the error rate, so to add some noise resistance to our system. And let's see whether we have succeeded on this or not. So this is a valid logical Z operator, right? And but again, it's very easy to see that this operator here is a valid logical Z as well. And how can I see that these are actually equivalent? It's easy. So if I have this logical operator here, I can add identity, because you can always add identity to your system. And what you obtain is an operator like this, right? And this needs to be equivalent because this is logical Z. and this guy here is the identity, so they need to be the same. And as you can see, you know, adding this square, I can modify the path. The important thing is that it always gonna percolate the lattice from top to bottom. And what you have is that in this square grid of qubit, you have actually a lot of different representatives of the same logical operator. And this tells us that we have actually added some redundancy. Before, when we had the state of one qubit, the Z operator, we had only one. So there was only one way to apply Z to the system, which was exactly Z1. So Z on the only qubit that you have. Here, you have multiple copies of the same logical, which means gives you the intuition that if you have to measure your system at some point, you actually have more than one choice. And as a consequence, you can infer that you have actually added some redundancy. So, okay, it's clear that we have more than one copy of the same logical operators on this lattice, and they all obtain from the first one by adding some identity, the stabilizers. So let's see whether we are actually able to do error detection or not. So let's suppose that I have an X error here, and we have a bunch of operators that we can measure to detect errors. So the operators were the blue vertex operator or the orange faces operator. So let's suppose that we have a blue kind of error. Anyone knows what should I measure to detect for this kind of errors? Like I have two choices, blue vertex and orange face. Anyone knows what should I go for if I want to detect for the presence of this error? Yeah, great. And so you can see that if I measure a bunch of orange operator, like, will this one give me any idea on the state of this error? No. But what happens is that if I measure, for instance, this one, then this is going to be lit up. So, okay, and this one as well, right? This one, not really, because it has overlap too. So this one, and that's it. And similarly, so what I'm saying is that whenever I have a blue kind of error, like this one, what I can do is I can measure the plaquettes that are on the system adjacent to it. And what I'm going to obtain is that all the plaquettes that have odd overlap with the error itself are going to tell me that an error is present. And similarly for the yellow error, I can measure the X operator. And what I'm going to have is that, okay, this one has even overlap, so nothing. I will have this one and this one, which I mean the operator that I support on these 4 qubits, that is going to tell me that something is odd with my system. So by measuring plaquettes and vertex operator in separate round, I can detect for the presence of poly error on the system. Great. And what is the fact that I can do this in 2 different, let's say, round, it's because the planar code is a CSS code. So a CSS code is just a stabilizer code for which the identity, the stabilizer group, can be written as a product of a bunch of X only Pauli operator and Z only Pauli operator. So I have these two separate sets that I can measure, and they're gonna give me information on error of the system of the other kind. Because of course, if I have a blue kind of error and I measure the blue kind of operators, they always gonna commute, so I will not have any information on this error present on the system with that. And in general, as we have seen yesterday, we have a qubit that we have encoded with a bunch of physical qubits. We have a stabilizer group that is the identity. And what I do to detect for the presence of error is I measure these operators. And whenever I have all plus one, I know that I'm in the code space. So there is no error present. And whenever I have at least one minus one, I found one operator that anti-commutes, I know that something went wrong. And CSS codes are just exactly the same, but Z and X operator are distinct, meaning that we have seen the example of the 513 code. And today, I'm only going to talk about codes that can be described by a group of identity that is made only of Z or made only of X. And to detect for the presence of error, I'm going to do 2 rounds of measurement, one of the Z and one of the X. And this is, you may think that you are losing in generality by restricting yourself to look at CSS codes, but that's not the case, because up to scalar factor, we don't care very much about. Any stabilizer code that a stabilizer group that is mixed can actually be mapped to a CSS codes with the same asymptotic scaling. So we are good. We're gonna only talk about CSS codes, and so probably always only gonna refer to one of the two parity check or stabilizer generators and the rest of the morning. Just a small recap, because I don't know how much we have used that before, but as we have seen yesterday, we can map Pauli operator to binary strings. So yeah, if I have something like this on 3 qubits, x1, x2, this can be mapped to 110. And similarly, I can do the same with Z2, Z3. It can be mapped to binary string when I put a 0 if the operator is the identity, and I put a 1 if the support is non-trivial. So in this picture, I can write like an arbitrary Pauli operator as a string with 2 and bits. And what is nice is that thanks to this symplectic product here and this matrix as we're gonna call omega, once I have I can check the commutation relationship between two operators only by looking at this symplectic product on F2. So what I'm saying is that in general, you can write an operator like this. We can concatenate the two strings, the first one that represents the X support and the second one that represents the Z support, and you can write something like this. And so our problem of commutation and description of the Pauli operator is actually now mapped to a bunch of 0 and 1, and we can use all the linear algebra that we already know. And what is important is that, this is very similar at this point. What you want is that whenever you have a stabilizer group, you can describe it in this symplectic form, like this. And then you can check if it commutes, when I mean the product of H and H transpose, so it's the parity check matrix, and yeah, should be precise since I introduced omega. which is actually the operation that tells me we don't care about how much two X operators overlap, they're always going to commute. I'm only care about the overlap between the X and the Z part. This is what it's telling me. And so not only when you have to define the stabilizer group, but also when you have to detect for the presence of error and define a parity check, the only thing you can do is that you can have your error, your system, and then check at the commutation relationship with the stabilizer. And this is going to give you the syndrome as a problem on linear algebra over F2. And this is actually very similar to what happens in classical error correction, where codes are defined, linear binary codes are defined as parity check metrics. So does anyone know what this parity check matrix is the code of in classical error correction? So we can, it's the repetition code. So what I mean is that in a parity check, I'm gonna draw one check for each row and one edge for each column. So here I'm gonna have 3 edges. Edges are bits. And so, you know, you can I have 3 bits in this code, and then I have let's write it in a different color. 2 checks. So check number 1 connects bits number 1 and 2. So I'm gonna put it here. And check number 2 is gonna connect bit number 2 and number 3. And so this is the graphical representation of this code here. And it's called the repetition code because it maps for this code. It's easy to see that all the code words, as we have seen yesterday, are in the kernel. So commutes with the parity check. So we have this relationship. And for this matrix here, you can easily check that we only have 2 valid code words. And these are the 2 valid code words. And this is the easier classical error correction code. And it's just, you know, the repetition code, because basically you can say it encodes 1 as 1, 1, 1, and 0 as 0, 0, 0. And what, so it's clearly seen why it's called repetition. And it's also clearly seen how can you correct and detect for errors. So if you receive, for instance, the word 101, what do you think is the input code word once you receive this word? Any taker? Yeah, great. So that's a majority vote decoding. And this is actually how you can decode for the repetition code. So you can do a repetition code as big as you want. You know, I could have, and if I have more, I can correct for more errors. And to decode, you know, the best you can do under like a reasonable noise model is just to do a majority vote. And what you're actually doing is that, let's suppose that you have this this graph here, and this bit, as in 101, is flipped. When you measure the parity between bit 1 and bit 2, so you check whether they are the same or not, which is equivalent to multiply the string by this binary vector. It's just telling you, check that the parity of the first 2 bits is the same. This is gonna tell you that something is wrong. And when you do for check number 2 tells you to look if the parity of bit number 2 and 3 are the same, and again, it's gonna lit up again. So in the repetition code, again, we have this situation where we measure some checks or classical codes, and we're going to detect for the presence of error. And this is what is done, like classical error correction. Binary codes are actually described by parity check matrices like that. Code words are all the vector in the kernel, so which means vector that multiplied by the parity check are 0, and the syndrome itself, when it's non-zero, is the multiplication of the parity check by the state of your bits. So it's again a binary vector like that. And thanks to the symplectic representation of Pauli operators, we see that we can have like the same description of CSS codes in terms very similar to this. So let's see. It looks like for now, the two problems are very similar. So maybe my matrix is a bit bigger and I don't have to, and the product is, I have an omega in the middle to remember for the X and the Z, different commutation relationship, but it looks like the situation is very similar. However, there is something that is peculiar in quantum coding theory, and we don't have the same in classical error correction, and we can see what that is called degeneracy. So let's take a Z error like this, and then, you know, the syndrome for this Z error is these two vertex operators here are the only one that have odd overlap with what I draw. However, let's suppose that something else flips in the system. So I add this Z error here. So what is the syndrome of this new error that I draw? Can you see any? So, okay, it's an orange error, so I should measure blue operators. Is there any operator that has odd overlap with this bit of the error? No? Okay, great. And in fact, the syndrome of the error that was there before, without this, you cannot see, without this guy, and this error is the same. And what is true is that actually I can add, you know, any kind of stabilizers, and the syndrome is not going to change. And, you know, it's not only things that are disjoint like that. What I'm saying is that the syndrome of this error and the syndrome of this error are actually the same. And this is not something that happens in classical coding theory, because following the same notation that I did before, where bits are edges and checks are little circles, you can see that, you know, no matter each error has exactly one and only one syndrome. So there is no way I can keep the same syndrome but changing the error if I'm always below some sort of threshold that is the one we are interested in by now. So this phenomenon is called degeneracy, and is very important when we have to decode our syndrome information and find a recovery for the system. Because, so the only information that you're gonna have when you want to decode and recover your system is the syndrome itself. So we're only gonna be aware of this guy and this guy. And so how can a decoder, which is a classical algorithm that takes an input, the syndrome, and gives you a Pauli operator that is the recovery and the correction, how can that compute the optimal solution? So what is very important here is that if the decoder gives me an output this string only, or this string plus this phase, it doesn't really matter, because as you remember, this guy here is the identity. So actually, you're not changing the state of your system. And here is the same. This operator here and the operator like this are equivalent because they only differ by an operator that by assumption is the identity in the system. So this means that we have some chance of being able to correctly decode our information, but maybe some care is needed. So we have a lot of errors that are equivalent, they give the same syndrome, but they actually have the same action on the system, but a decoder needs to pick one once it gives you an output. And this is, the degeneracy is what makes the decoding problem for classical error correction and quantum error correction in the CSS setting like this different. Because let's suppose, let's take the easiest noise model we can think of. We're gonna say that each bit or qubit is gonna be flipped with probability p, and is not gonna be flipped with probability 1 minus p. So in this noise model, you know, the probability of the error E, here is the support of E, and here is the cardinality, is given by this equation. Okay, so with some probability I flip a bit, and with some other I do nothing. That.
So why does it actually matter if so the bottom left two examples, you're saying, okay, the error signal is the same, but doesn't it matter what I do to correct it? Like, if I can always just apply the three Pauli Z operators, and I mean, they differ by identity, as you said, so it doesn't matter.
You are very right. So it doesn't matter which one of the two you pick. It only matters, like, if we manage to arrive at the end of this slide, you can understand why this gives you two different frameworks for decoding quantum codes and classical codes. So the fact that you have more than one error with the same syndrome, it means that if you want to minimize the weight of the error, for instance, which is a sensible option when you have this noise model, you can have error class that has a lot of different representatives like this, that it's actually more likely than the one that has exactly the straight path. I know now it's confusing, but I'm gonna make it clear now. The problem was just exactly like, you can decode these two things in two ways, and this is gonna be, you're gonna be fine in both cases. But it's not always easy for an algorithm to minimize for such a quantity. Yeah.
To recall this question, I don't get it. Why, if we the errors, if we correct for the straight one or for the straight one plus an identity, we get the same correction, right?
Yeah.
You say. Then why we need to care about minimizing weight in that case? There are still, I don't know, maybe examples where if we don't minimize the weight, or we can have like errors that can confuse with logical operators, maybe, I don't know.
Yeah. I'm gonna present you the difference between two different decoding strategy, and if I convince you that that was an interesting thing to observe, then we go on. If not, we go back. Okay. Okay, so we are back to this like noise model. So in this noise model, the most likely error is the minimum weight of one, right? If P is smaller than 1/2, the most likely error. So if we decode using this maximization function, whatever, so we pick the most likely error, is going to be the one of minimum weight. And in the classical setting, this is the case. The problem is, as we have seen, that in the quantum case, because of degeneracy, we have an entire class of errors that have the same syndrome. So this is maximum error probability that agrees with the syndrome. Sigma of E indicates the syndrome, so that is actually solve your problem. And we know that we have a big class of error, sigma E, such that it has the same syndrome. So in the quantum setting, this set here, so I have all errors. I take one error that has syndrome S. Let's call the syndrome in another way, sigma. Then all the errors that are in this class are so this is the stabilizer group. So all the operators that act as the identity on your system are going to give you the same syndrome. And as you can see, like how many, if your stabilizer group, as dimension, as m generators, this set here is big, like exponentially big. It's like 2 to the n. And what happens is that if I use the same decoder that only gives me the minimum weight error, it can happen that the minimum weight error is not the error that also maximize this probability. So the minimum weight error could belong to a class of errors. You could have the situation when you have a class of errors with a lot of medium weight errors whose global probability by this sum is actually lower when I sum over all of them of the probability of the minimum weight. So what I'm saying is that you could have a situation where the minimum weight error, which is like, let's suppose, this is not going to be the real situation because the real situation is a bit complicated. So I don't know here. This is the minimum weight error, let's suppose. And then, you know, there is a non-equivalent error, like non-equivalently on the logical level. I'm gonna use the red for this one. So something like this. This is very clearly very wrong. So these two errors are different logical level, but it could be the case that the minimum weight error doesn't belong to the class that, you know, by summing all of the error up to stabilizers is actually lower. So by summing a lot of this guy here, it could be the case that the minimum weight error is not actually the most likely because you sum over an exponential amount of errors, and the sum of each guy in that summation of each factor, maybe this class here doesn't contain exactly the minimum weight, but all the others are small enough. So, you know, maybe you have the minimum weight as probability as weight 2, and all the other errors equivalent up to stabilizer in that class have weight 8. Let's suppose that you have 2 stabilizers, okay? So your probability in total is this big. And then you have the other class, where the minimum weight error in the other class is like 3, and all the others are like 6. So in this case, minimum weight decoding is going to give you the class of the error of smallest weight. But to actually do the maximum likely decoder, so even a syndrome minimizing over the probability of the class of error, you're going to find that the one that doesn't contain the minimum one is taken. Is the example convincing more or less? Like what I'm saying is that you can have like an entropy factor against the minimum weight. So the minimum weight could be in another class with respect to.
Yeah, I just want to clarify, is the reason we're minimizing the weight over the whole sum just based on the idea that it's more likely that less errors happen?
Yeah, so this is the noise model. Yeah, very, I should have made that clear. That's very important. This is my noise model. So my noise model is described by this equation that says basically that the lowest weight error is the most like, yeah.
Okay, and does this change if we're performing these checks less frequently? So I assume at discrete time points you're performing this check, right? And if you're doing it spaced further apart, then it might be more likely that
Yeah.
a non-zero amount of errors happen.
So that if you start by this noise model anyway, again, you will have the same assumption just if you add some more time, but it's tricky. You can do that. So, and of course, if you leave your system there for more time, you probably expect more errors. But again, like you will expect the minimum weight to be there again, just by summation bound. And you may want to do that, but you also have to be aware that your system is going to have like a maximum amount of noise that can afford. So yeah, skipping around the error correction, like, yeah, it's not always effective. So you could, yeah, because you could reach a threshold after which you're not able to recover the system anymore. So
So the problem of degeneracy here is not when you talked about it, is that coming from the fact that multiple errors can have the same syndrome, or just that like you have these error classes in the quantum case as opposed to the classical? Like, are there?
so
This is suggesting then that there are still errors that are not like the identity multiples of each other that have the same syndrome still?
So the degeneracy itself is just the fact that multiple errors can have the same syndrome. And you're right that I've not introduced like different logical errors, but that's what I'm saying is that here I'm just summing over things that are in the stabilizers, actually here.
Mhm.
So I'm not considering errors that are not equivalent. So I'm saying this is, and then the decoder, like these two classes that I haven't defined, like you're right, are gonna not be logically equivalent. Otherwise, it will not be a problem. So what I'm saying is that this is error 1, and this is error 2, and error 1 is gonna be equal to like logical X. No, we are doing Z. So logical Z times error 2.
Okay. And so so you can have different logical errors that still have the same syndrome.
Yeah, yeah.
Okay.
Yes, yeah.
Thank you.
And this is what the decoder is gonna do. Like the minimum weight one is just gonna decide in between, like find the minimum weight error that has that syndrome, and then you can look at his other logical representative by doing something like this.
Thank you. That makes
Thanks.
sense now. Thanks.
Okay. Okay, so the decoding problem for quantum and classical coding theory are a bit different. So the optimal decoder in quantum is gonna minimize over all equivalent errors, so the class with all the stabilizers. This is a very computationally hard problem because I have 2 to the m stabilizers. So computing the sum of probability for each element in the stabilizer is very expensive. However, it's probably, without probably, is good enough in most cases to only look for the minimum weight error, which is the error most likely. So for instance, the decoder that gives me just the minimum weight error that explains the syndrome, which is 2, without looking at all its equivalents in the stabilizer class. In classical coding theory, these 2 problems are the same because we don't have any degeneracy. And that's good enough. Now, yesterday, Philip introduced, the magic parameter in error correction with our N, K, and D. This is classical. Let's do it quantum. And D is the distance, which means the maximum amount of errors a code can tolerate. If a code has distance D, no matter what, there always gonna exist 1 error of weight D over 2 that I'm not able to correct, if not by luck. What happens though is that if your system has n qubit and you have the stochastic noise model where each bit is flipped with probability p and not flipped with probability 1 minus p, on average, the probability of flip is p and your system has n qubits, what's the average number of errors you expect to happen on your system? No? 1 on P. 1 on P. I don't know why one on P. But you have n things that can go wrong with probability P. It's Pn. I don't know why it's 1 on P. Whatever. So, and Pn, it's very often, very quickly bigger than D. But what is also true is that we can take the planar code as an example, is that with some percolation theory, if you randomly flip some of your bits, and so with 1 round, Pn are gonna be flipped, what happens is that you're probably gonna have region of errors that are separated. What I'm saying is that the error that you cannot correct is this one, because this is illogical. So this is, this as syndrome 0, you don't see that it is this as happening. Or as I said before, any error that percolates the lattice. But what happens in reality is that just by some percolation argument, if something goes wrong in a system like this, it's very likely that error are gonna have this shape. So I'm gonna have P and errors, but they're not gonna be, so it's very unlikely if you just flip a coin randomly, 1 for each edge, that you're gonna have this configuration, this very ordered and nice configuration, right? What happens is that in a system like that, you're gonna have regions of error that are separated, right? So you're gonna have clusters of error, and clusters for P low enough are gonna be small, and you're gonna be able to correct them if your system is good. Like this is just and it's very clear that if this lattice here is a giant planar code of distance I don't know what, but you can, if you have the syndrome of this things here, it's very easily seen that if you just look at the syndrome and try to find the minimum weight error that deletes the syndrome, you're gonna get rid of all of them without problems. And this is the idea that allows us um, to prove that some good codes have a threshold in general, and also to understand what a threshold is. So one, together with n, k, and v, code parameters, so length, dimension, and distance, an important figure of merit for codes is the threshold. So the threshold PT is a probability. So you take a code family, which is already confusing as a concept, but with the planar code, it's easy. You take a planar code of distance p, and then you go d+1, d+2, and so on. So you take figure and linear planar code, a family of codes. It's just a set of codes that for growing n have a growing distance as well. And we say that that family of codes has a threshold if there exists a probability p threshold, such that for noise probability below this number, by growing the system size, I can also decrease the failure rate of a decoder. So a threshold is usually it's referred to a threshold of a code family, but actually, if you tell me that your code family has a threshold, you should also give me a decoding algorithm. So I take a decoding algorithm that does some fine set recovery and a code family, and I ask myself, there exists a probability such that for all noise rate below that p, if I increase the code size, the probability of my decoder to fail decreases. And if this is maybe the most effective way to understand what a threshold is to look at the threshold plot. So what I'm saying, this is, yeah, I think yeah, it doesn't matter. It's a threshold for, I think, the planar code. It's a very elementary one, not the best one, not the best decoder. It doesn't matter. What I'm saying is that a code family, see, I'm studying codes with increasing distance here. And they say that a code family has a threshold if below some, here there is a crossing point, and as you can see on the left-hand side, the bigger the system, d equals 30 means that you are bigger, the lower the error rate. Logical error rate is the probability of failure of the decoder. And above the threshold, if you increase the system, things gets worse. So the fact that codes can have a threshold means that if we want to decrease our rate, logical error rate, or noise, logical noise, I mean, if you want to protect your qubits better, you can just increase the size of your system and be sure that you can decrease the probability of error. So at the beginning, we wanted to add redundancy to a system to decrease, so that we had on our new system made out of logical, a lot of physical qubit, we had something like, so the probability of error on our encoded system was lower than the physical one. And this is the existence of a threshold for some family of codes is what allows you to do. And the idea of why this is possible is exactly that, is that if you have a system, so and you have a noise model as the local stochastic noise model, error are going to be made in this joint cluster. So you can probably locally decode for those. And in fact, well, I would say the best, no, I don't know, a minimum way to decode a very good one for the planar code is only the perfect matching decoder. So let's suppose I have the syndrome only. And so I'm gonna draw some syndrome. So the most important thing is that in planar code, we don't care about the boundary conditions, but each error is gonna lit up an even number of syndrome. And the minimum weight decoder gives you the recovery that finds the minimum length path in between the two syndromes. So it corrects like this, this like this, and this like this. And this is exactly the example of a threshold of the planar code with the matching decoder. And the fact that errors are separated means that I only need to look at the local information on the syndrome graph. So local, I mean, you know, if I know that there is a syndrome that has lit up in this region, I can just look in my neighborhood bigger and bigger to find my other syndrome that the same error has lit up. And the fact that I can correct locally in separated clusters is what gives assure me the existence of a threshold and the ability to correct for this amount of error, which is what I expect in my system. Okay. So great. We have seen that the planar code actually has the redundancy that we need. We can correct for X and Z errors. It has a threshold. And yeah, intuitively, I also mentioned you what a decoder that works very well can do, just finding the minimum weight path in between two syndromes. What else? So to conclude the picture, it's probably worth doing a step closer to the qubits. I remember that I've talked about stabilizer measurements, and I've said, yeah, we measure the stabilizer and we have the syndrome. What we have to be aware of is that stabilizer measurement is, you know, we are dealing with qubits and we do need to perform some operations to actually find out this, the stabilizer itself. And this is relevant because, you know, every time you touch your qubits, it's likely that you're going to introduce some errors. But so as you probably know, let's suppose that I want to measure this stabilizer here, like just a phase operator. What I do is that I have my qubits. No. I have my qubits that are edges, right? And what I do to understand whether these 4 qubits are in the plus or minus 1 against state of the ZZZ operator, I do a bunch of scenes, right? Right? Well, this is an auxiliary qubit. So what I mean is that to actually measure the stabilizers, what I have to do is that I have to add an auxiliary qubit to my system and then do entangling operation between the support of the stabilizer itself and the auxiliary qubit, and then measure out the auxiliary qubit. And this is how you do stabilizer measurement, which is everyone okay with that? Yeah. Yeah. Okay. And And this is, it can be tricky because yeah, you're doing C naught between an auxiliary qubit and your data qubit, or the qubit that encode your code space. And first of all, you have to be aware that you can spread more errors. This is not what we care about, but what is important is that you need to be able to perform these operations. And that's actually the reason why everyone loves the planar code, because when you have to do a C naught between two qubits, you need those to be connected in a way. You need to be able to do an entangling operation between those two qubits. So this, I think, IBM chip, very old, only 4 qubits, or five, sorry. It's exactly a plaquette. This is like 2019 Google layout of their Nature quantum advantage experiment. And these gray things here are qubits. Those guys are, I don't know, they call anymore. Anyway, they are the things that allow you to make operation between those two qubits. And this is a tiny planar code. And what you can see is that this is the easiest maybe architecture that you can have. Quantum computer, you have only connection between one qubit and 4 neighbors. And it's exactly the kind of situation that you need to measure a stabilizer in the planar code. What I'm saying is that, to measure the phase operators on this planar code here, you just need to add six auxiliary qubits and do a bunch of C naught like this, right? This is how you measure the stabilizers. And what is nice about the planar code is that with connectivity easy as this one, you can do it. So, I can say this is an auxiliary qubit now. I'm going to use it to measure Z operators. And now I'm going to do something that is not correct, but it doesn't matter. So I think I have to alternate the other ones. But what is important is that with this simple architecture, I can measure the stabilizer of the planar code just by requiring connectivity between qubits that are close by in a square grid. And it works the same for the Z operator, right? If I want to measure this guy, so this is I don't want to go into the details because I'm going to draw something wrong. What I'm saying is that in this grid, I can color my qubits in a way so that each qubit is either an edge qubit, a data qubit that encodes information, or an auxiliary qubit either for X or Z operators. And by only requiring close by qubits to talk to each other, so C naught between close by qubits, I can extract the syndrome and perform syndrome detection and therefore error correction.
What's the effect of maybe having an error also on the ancillas? So if you have an error on the ancilla, then
yeah, very good. So there are two kinds of error. One is, let's suppose that you have an error on the ancilla. So like this ancilla here tells you that the stabilizers is perfect, while actually it was flipped because you had an error, an error here. So by chance, basically the ancilla says 0, all good, we are in the +1 eigenstate, but actually there was an error. So this is a problem. And what you actually do in real life, you measure the ancilla over and over again. you don't do one round of error correction or stabilizer measurement, you do more than one, so that you are confident. You can do like the majority vote. You measure your ancilla 5 times. Depending on the probability of error, you can infer that. And that is actually something like, I hope we will talk about at the end. Then there is the other problem, but I will not fully not mention. There is not only that problem, is you can do this circuit, yeah? If an X error on the ancilla happens here, this propagates, like C naught maps this X here, and then here and here. So basically you had maybe no error on your system, you do the C naught to measure the stabilizers, and the error is spread to your data qubits. So that's a problem as well. And in fact, what is people are probably looking at more is to look at the error correction picture as a whole at the circuit level. So instead of looking, you have a code and then you give me a circuit to measure the stabilizer and so on. We look at the whole measurement error correction cycle that includes the logical operation, but not only, also the measurement. You can add more qubits, more auxiliary qubits to detect for errors that spread over and stuff like that. But it's, you know, you can use the same tools that you use in error correction to take care of those problems.
Can I ask a second
Yeah,
question?
sure.
Would it be possible to have also like an ancillary setting, or that would be too slow? I don't know, like for example, in the GKP code, there is the ancillary setting, and then you are measuring the other stabilizer. I mean, the picture of the GKP code, like the other stabilizer.
Yeah, this is what,
Oh,
so I'm not a physicist, neither an experiment expert, but yes, this is what is done. So what I'm saying here in this picture, the connectivity is different between X and Z. So I think the best is to map X auxiliary qubit and Z auxiliary qubit into different one, but at each round you have to reset.
Okay.
And of course you can use your auxiliary qubit to measure the same things more than once. And yes, as you said, that's kind of expensive to reset the auxiliary. And also, yeah.
So if you have a different architecture that isn't perfect for the planar code, for example, does that mean you're doing a bunch of swaps in between to kind of like
Yeah, so I took this is superconducting qubits, both IBM and Google, just because that's the motivation, because we have studied probably the planar code so much, because it's easy. And apart from this kind of architecture, there are also, you know, other problems that are maybe the reasons why we always want one qubit to talk to as little other qubits as possible. Then in ion-based quantum computing, you can have the swap to make qubits that are not close by talk. In cold atoms, you have some flexibility as well. So this is not the only architecture possible. It's just, yeah, one that we have seen and studied a lot. So I don't think that's necessary. Like, I hope we can go behind the planar code for a lot of reasons, but this is why people love it.
I thought IBM currently has like a heavy hex architecture that doesn't look exactly like the previous.
Yeah.
So can you still run the planar code without swaps?
Yeah. Yes. And also they are also studying like for other codes, and there are ways where you can map a code that doesn't require local interaction between the qubits to like a limited connectivity graph. So people are trying to do other things. It was just an example to justify the love for the planar code, I guess, because it's not by chance that Philip talk about planar code. I'm talking about the planar code. I think every error correction talk you're gonna hear is gonna be in a way or another about the planar code. Okay, so yeah, the problem of the connectivity and the architecture. So this is why the planar code, we like it. So as this property where I can actually easily do syndrome extraction and the operation between the qubits that are necessary to protect my system from the error. However, there are reasons why we should go beyond the planar code, which is the goal, the ultimate goal here is to perform fault tolerant quantum computation with constant overhead. So meaning the overhead can be quantified as, let's suppose that you have an algorithm that you want to run, and that takes k logical qubits, and how many qubits, physical qubits, are you willing to pay to actually be able to run in a reliable way your computation. So you want the proportion between the physical qubits you actually spend and the logical qubit you are in theory using to be as small as possible, constant, right? And the threshold theorem says that that's possible. So it's possible theoretically to achieve fault tolerant quantum computation with constant overhead if we have basically, roughly, the theorem is more involved than this, but in a nutshell, LDPC codes, which means low density parity check, which means the stabilizer group, each stabilizers has low weight, so the support is small, and each qubit in the system has a small amount of stabilizers is involved in. So if we look at the symplectic picture of the matrix, that translates into a low density parity check, which means a matrix of 0 and 1s with a low column and row weight. Constant rate, so the rate is this thing here. When you have a family of codes, you do the limit between the logical qubits that you have and the physical qubit that you use. And this is the rate. And an efficient decoding algorithm and the threshold. So efficient means linear, like matching that I've seen before is n cube, worst case scenario, but actually, you know, it can be parallelized. Like you could almost say that it's linear, it's okay. And the threshold, meaning that you need to be able to, if your algorithm becomes longer and you need lower error rate to run more gates, you need to be able to scale up your system to lower the error rate. And you know, the planar code as is an LDPC code. What do you think? Is it? Is it not? Yeah, yeah, yes, it is. Efficient decoding algorithm or threshold. Yeah, yeah, threshold, we have seen it. The efficient decoding algorithm, we have that more or less, or you know, we don't care about classical resources that much. We can assume that are for free. The problem is the constant rate. So I can do a planar code as big as I want. I'm gonna increase the distance, but I'm always gonna encode only one logical qubit. So the rate, the limit, k is always 1 and it grows. So the rate goes to 0. And that's the reason why we should, you know, look at other framework or codes to protect our information, because we know that the planar code is not enough to actually scale up our computation. And the good news is that good codes actually exist. I want you to notice that the results are all from 2021 onwards. So a good code is good, comes from classical coding theory. So a good code is a code that for which the rate is constant and n and d, so both k and d grows linearly with n. Okay. And yeah, that's it. This is what a good code is. K and D grows with n. So you have the maximum efficiency, right? Because you only pay a constant factor to encode your qubits, and your distance is as good as it can, because yeah, you cannot have more than that. And it has not been easy to find LDPC codes, so codes for which one qubit only talks to a small amount of qubits, and yeah, and the check only contains a small amount of qubits that were good. So 2021 is like yesterday, and we know that these codes exist. That was an impressive result. And what we also know is that these are all asymptotic results. So when you actually try to build any of these codes for small scale, like the last Google paper had a planar code of distance 7 with like 49 qubits in total, whatever, it's not, you know, it's quite small. And the problem is that these codes becomes like, are good, yes, but in the asymptotic limit. So maybe you have to go to thousands of qubits before finding some actually improvement with respect to the planar code. And what this code construction give up in order to obtain the good parameters is the locality. So, and by locality, I mean, you know, I've shown you how you can, on a graph, on a connectivity graph, you can map your qubits to a connectivity graph, so that for syndrome extraction, basically, you only need to talk to nearby qubits. And the locality is basically that. For each code, you can define a tunnel graph, which means I put one kind of check for each bit and one kind of check for each one vertex for each bit and one other kind of vertex for each check, and I see the connection between them. So what I'm saying is that, you know, each code you can define, given the parity check, you can, for each row, you can define this out the check. For each row, you draw a new vertex, and then you have for each column, which are qubits, you drive another kind of vertex, and then you connect the two if you connect a check and a qubit if they are contained in each other. So for instance, this is it's better easily done like this. So before, that was another representation of the tunnel graph. Here I have 2 qubits. What I'm saying is that you can map a code to a graph, and that is what locality means. So you embed your code either in a 2D or 3D space or whatever graph, and then locality means whether you have a finite radius of interaction for all the encoding and decoding operation. So good codes exist asymptotically. You have to go very big to find improvement with respect to the planar code, and they give up locality. So, you know, not exactly the picture of the grid hexagonal or not that we have seen. Yeah, so I think that's all of this to say. It's important to go beyond the planar code, and this is a direction that both on the theory level and on the experimental level has been pushed in the past few years quite a bit. I'm not going to talk about this good codes construction, because they are quite complicated, but what is common to all of this code construction is that they all come from a product, tensor product with 2 codes, are all CSS codes, and yeah, and all can be described in a way or another by chain complexes and so on. So I will not talk about the good code itself, but I'm going to talk about hypergraph product codes, which, you know, have all the things that are needed by the threshold theorem, and basically give up the locality of stabilizer to obtain the constant rate. And as you can see, also they can be making robust against noisy syndrome, but we'll see. And spoiler, the planar code itself is an hypergraph product code, but it's 4 minutes to midday, so we're gonna talk about them later. Yeah.
So why couldn't you just take multiple planar codes? Like if you want k logical qubits, take k planar codes, and then I
This
don't
is
see the
what, you know,
Yeah,
like
that's-
quite a few architecture have been proposed in this direction. Like we can do universal computation with the planar code, and of course, this is what you do, but your rate, your efficiency is not going to improve. You're always going to spend n or d squared qubits to encode 1. So if you have a linear relationship, so let's suppose that you have a good code that has n right? And then let's suppose that you want to, so fix a k, you want this. And then for the planar code, you need n 1, that is square root of n. And you need k of this. So, and if you also want the same distance in between the two, your total cost is going to be more. You're not convinced?
I mean, isn't the distance is per planar code kind of, right?
Yeah, but let's suppose you have your algorithm, you need k logical qubit.
Yeah.
With distance alpha n. So alpha n is surely bigger than square root of n, right? So to obtain the same scaling, so same distance and same k with a planar code, you need more. So here you can have 1 or 2 block codes that have these good parameters, but if you have to do the computation,
I mean, I see the problem with the distance somehow, but is it really like a problem in practice? Because like each, let's say I make for one logical qubit, I have one planar code, and I make this large enough that it's robust, essentially.
Yeah.
So I take an n that is sufficient.
yeah, okay.
And
You
now
have
I
one.
and now I take two of them. What is the problem now?
The problem is that you are gonna have, again, like for instance, here the distance scales, the distance of the planar code scales as a square root of n, right?
Yeah.
And so I think we can, I can do the computation. Like what I'm saying is that let's suppose, how many qubits do you want?
I mean, I take n as large as I need, such that
No, okay, that
it's-
the distance is okay, but then how many planar code you need?
I mean, however many logical qubits.
Yeah. So what I'm saying is that if you want k logical qubit and distance d, whatever, so on one end you need, so for the planar code you're gonna need physical qubits that scales k times d square. So you need k, you want k logical qubits with your planar code, right? So you want k, and d square is how the n scales because with some distance.
Yeah.
Whilst if you have like a code good enough, you need n, which is equal to uh, 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 d over alpha, which is also equal to k over beta. It's probably like the scaling, the asymptotic scaling, what you pay is more.
Yeah.
What I'm saying is that there are proposals of architecture in that direction. There are a few, like, if you have your giant grid full of planar codes, and then maybe, you know, you have logical qubit 1 encoded here and logical qubit 5 encoded here, and you have to do an operation between the two. What do you do? Like, there are ways to do that, but basically you have to use a lot of auxiliary qubits to entangle the two. Like, it doesn't scale the best possible way. It's possible. It's not very efficient.
Okay.
If you want to, yeah. Okay.
There's no more questions, then let's thank Armanda again.
So now we have the typical lunch break, so we can proceed from that, and then Armanda will continue on her lecture in the next half hour. And it seems Jake needs to say something.
Yes, I would also remind people that after Armanda's session at